Welcome to the Deep Dive. Today we're going to try and understand the invisible heart of modern industry. We're talking about the huge world of critical rotating equipment.
Right.
You know, the motors, the pumps, the compressors, all those massive cooling fans that keep everything running, from oil and gas production all the way to, say, your city's water supply.
And that's really the core truth here. These machines, they very rarely fail without some kind of warning.
Some kind of warning.
Yeah, long before you hear that catastrophic, grinding sound, they're communicating. They do it through these really subtle, tiny patterns, vibrations that signal there's something deeply wrong.
And that is our mission for today. We're doing a deep dive into a whole stack of sources. We've got success stories, technical papers, some product innovations, and they're all focused on solving these invisible mechanical problems.
Right.
These are the subtle movements, the hidden dynamics that our own senses just completely miss. But if you ignore them, they lead to devastating breakdowns. We're talking massive, multi-million-dollar costs in downtime.
And the stakes for reliability really couldn't be higher. If you miss those early signs, those critical signals, a small internal problem it can escalate so fast
Like what?
into severe equipment damage, unplanned outages, and, serious safety risks. So the goal here is to find technology that replaces that old, costly guesswork with real, data-driven certainty.
So we're speaking directly to you, the person who needs to know about this, whether you're maybe prepping for a reliability meeting or you're just curious about how the modern world actually stays online. Our focus is on how experts, specifically a company called VibeFX, are using these advanced tools to literally hear what the machines are saying.
If you look at the data they provided, the big shift from reactive to proactive maintenance,
Yeah.
it really just comes down to measurement. How can you possibly fix something if you don't really know what's wrong?
Okay, so let's unpack that. Because,
Yeah.
historically, maintenance was all about instinct, right? The seasoned millwright could listen to a bearing or, I don't know, feel a housing and just know something was off. But modern machinery, the tolerances, it seems to demand so much more.
Oh, absolutely. We see this exact challenge laid out in the source material. It starts with a classic industry story.
Okay.
So a client was just plagued by this persistent vibration in a critical piece of equipment. Their crew, we're talking experienced millwrights, they went through all the standard
She's
procedures,
checking alignment, tightening bolts, all that.
all of it, balancing routine inspections.
Right.
But the problem it kept going. It got worse every day, and the financial pressure on the operation was just building and building.
So from the crew's perspective, they're doing everything by the book. They're relying on that critical instincts they've built up over decades.
That's exactly it. A millwright is trained to spot the visible symptoms, loose coupling, worn belts, bad mounts. They have that sixth sense.
Yeah.
But in this case, the millwright said the issue felt, quote, deeper, subtle, something structural. All their manual checks, all their troubleshooting, it just indicated that on the surface, everything looked fine.
And that has to be the most frustrating thing. You know you have a costly problem, but every manual check says the machine looks okay.
Right.
So this really highlights that failure point of just relying on human senses. If the machine looks fine and the usual fixes don't work, why should a plant manager trust a computer over the instinct of their best millwright?
That's a great question, and the answer is really scale and resolution. The millwright realized they had to, in his words, stop guessing.
Stop guessing.
Because human senses just cannot detect the data you need for modern equipment diagnostics. The issue wasn't the intuition, it was the tool set that they're using. And that realization, that's what leads us to the high-res diagnostic toolkit, vibration analysis and motion amplification.
Okay, let's start with the foundation then. Vibration analysis. We've all heard that phrase, but what's the story the machine is actually telling us now? What's different?
Well, vibration analysis today it's way beyond just measuring how much something is shaking. It captures this incredibly high-resolution data that breaks down the machine's complex movement into specific frequencies, specific amplitudes.
So it's like a language.
It lets the machine literally, quote, tell its story through measurable patterns. It gives you a clear, data-driven diagnosis for these common but critical faults.
Right.
Like, are we dealing with classic unbalance? Is it an early-stage bearing failure, maybe mechanical looseness or a coupling misalignment? The data turns that vague feeling of something's wrong into the undeniable fact of what is wrong.
Okay, but this is where it gets really fascinating for me. This is where you make the invisible visible. Motion amplification. I mean, if I look at a massive motor running, it looks perfectly still. How does this tech change the game?
Motion amplification is, It's transformative. It uses a high-speed camera and some very clever software to turn these microscopic, invisible movements into large, visible
So
ones.
like a thermal camera, but for movement.
Exactly like that. It reveals structural movements, component shifts that are just impossible to see with the naked eye.
You literally watch the machine moving, magnified.
Precisely. And the source material has this great example of its power.
Yeah.
So on a problem machine that looked totally sound, the motion amplification data showed a subtle misalignment.
Okay.
It was too small to see, maybe not even obvious in the vibration data alone, but it was severe enough to cause this destructive cascading effect through the whole system.
Wow.
That tiny, invisible wobble was powerful enough to cause premature bearing failure and metal fatigue across the whole thing.
That is a phenomenal insight, that a tiny wobble can turn into a huge expense. So motion amplification takes a machine that looks totally stable and just. It magnifies those hidden dynamics.
Mhm.
It turns what could be a month-long expensive mystery into a fast, precise fix. It's the ultimate shift away from just replacing parts randomly.
Exactly. It completely moves maintenance from being reactive, just waiting for the bang, to being proactive. And we should probably mention the toolkit goes even further.
Okay. These experts also use specialized methods like, say, infrared thermography to spot heat problems before they become failures. And they integrate predictive maintenance platforms with AI to analyze failure patterns in real time. It's a whole ecosystem.
So once you have that precise diagnosis,
Yeah.
then comes the second half of the problem, the fix.
Right.
And the approach is comprehensive.
Mhm.
If it rotates, they troubleshoot it, balance it, align it, and fix it. We really have to get into the real-world case studies now because they show the kind of radical efficiency that's possible when you start guessing.
And these success stories, especially the one from Interpipeline, they show that reliability problems aren't always complex. They're just misunderstood.
So let's start there. Case study 1.
Yeah.
A huge 5,000 horsepower motor pump combo at Interpipeline had been suffering from extremely high vibrations for 5 years, since the day it was installed.
5 years of lost efficiency, constant maintenance headaches, and, management pressure.
And the previous attempts to fix it were,
Mhm.
well, they were expensive and speculative. Incredibly so. Multiple engineering firms had looked at it, and they recommended these wildly expensive, invasive fixes.
Like what?
I mean, we're talking about suggestions like replacing the entire motor rotor. That's a $400,000 part, just for the rotor.
Wow.
Or doing structural geotechnical repairs, even trucking in gravel every year because they thought the whole foundation was unstable. It was pure, high-stakes guesswork.
But the Vibe Effects team, they suspected something else, something fundamental but often missed. A resonance issue at the motor's rotating frequency.
Which is so key. Resonance happens when the machine's running speed matches the natural structural frequency of its foundation or its housing, and it creates this destructive feedback loop that just magnifies the vibration like crazy.
So they used their advanced diagnostics, they confirmed it was resonance, and here's the amazing part.
Go on.
The full diagnosis took 1 hour. The permanent repair took only a few hours after that.
That's radical efficiency.
Yeah.
A 5-year multi-firm problem solved in an afternoon, and they avoided a massive capital spend.
And the result was the unit went back to optimal operation, hitting 99.4% uptime. They proved that what everyone thought was a component failure needing replacement was actually just a solvable dynamic interaction.
Between the machine and its foundation.
Mhm.
Incredible.
Now let's pivot to a totally different industry, water treatment. Case study 2. This involves new water pumps in 2 separate towns, Innisful and the Englishman River plant on Vancouver Island.
Okay.
Both had excessive noise, severe vibration, and it was so bad some of the brand new units couldn't even be used.
And in the Vancouver Island case, that problem went on for nearly 2 years. They had 4 different engineering companies and the original manufacturer all try invasive, expensive repairs.
The client must have been so frustrated. You've got community complaints about noise, you have equipment you can't use.
And again, everyone was focused on the hardware, on physical replacements or modifications that didn't get to the root of the dynamic.
So how do you fix severe physical noise and vibration without actually replacing the pump?
This is where understanding the electronic side is critical. The solution was all in tuning the VFD program.
The variable frequency drive.
Exactly. The VFD controls the motor speed by changing the electrical frequency it gets.
Ah, okay. So the VFD gives them flexibility and speed, but you're saying that flexibility was actually causing the problem.
Precisely. By capturing the data, they found that the speed they had programmed, the speed needed to get the right flow rate, put the VFD's output frequency at the exact point that excited the pump's structural natural frequency.
It was resonance again.
Resonance again.
So instead of pouring new foundations or swapping out pumps, they just shifted the required speed by a few hertz.
That's the elegant solution. They just changed the electronic driver program slightly to avoid that resonance spot. The result was immediate and dramatic.
I bet.
The noise dropped to acceptable industry limits, vibration levels plummeted, and all the units started running smoothly, actually exceeding industry standards, all fixed in a matter of hours. It just shows that real expertise has to include that electrical and electronic interface.
And when you look at the business value of these fixes, it's really impressive. We've got real numbers from the sources. Clients reporting a reduction in outlet gas temperature of 20 to 24 degrees Celsius after some fan upgrades.
And we have documented estimates that show comprehensive optimizations, including fan upgrades and things like pitch adjustments, led to a reported flare reduction estimated at $270,000 a year.
That's incredible.
When you stop guessing, the financial returns are just massive, and they're immediate. Precision work is profit protection.
Okay, now let's shift from maximizing runtime to protecting these assets when they're shut down, specifically fans. Because rotating equipment doesn't just have to run smoothly, it also needs protection when it's idle.
This is so important, especially in systems with multiple fans or multiple trains, like the big industrial air coolers you see in oil and gas.
Explain the danger here, this phenomenon of backspin.
So imagine you have a whole bank of fans. When you shut one down for maintenance, the massive airflow from the fans next to it doesn't just stop. It pushes backward through the idle fan.
And that makes it spin backwards.
Right. And if that reverse rotation gets too fast, you have what's called a backspin overspeed event. This puts enormous unintended mechanical stress on the whole system. You get premature bearing failure, potential coupling damage. It's bad news.
And it creates a huge safety hazard too, right?
A major one. If a millwright has to go work on a unit that has all this stored rotational energy from backspin, it is extremely dangerous. And that's where the DG2, that's where it comes in.
So what is the DG2 device? What does it do?
The DG2 it's a simple but very robust mechanical safety solution. Designed to be self-actuating. As the fan starts to reverse, the device mechanically engages. It's essentially a locking mechanism or a brake that stops the shaft from rotating backwards beyond a very safe minimal point. And crucially, it doesn't need any external power or complex sensors. That makes it super reliable in harsh industrial environments.
That's the beauty of great engineering, right? A simple, non-powered mechanical fix to a complex dynamic problem. So besides the immediate safety, what are the long-term benefits of installing a DG2?
Well, it significantly extends the equipment's life. It just completely eliminates that stress on the vital parts, the shafts, belts, couplings, that's caused by that unintended reverse rotation. But maybe the most important thing is it increases worker safety. It ensures that when a fan is shut down and a tech is doing lockout and tagout procedures, there's zero risk of stored rotational energy suddenly being released.
And VibeFX has a specialized fan division that supports all of this. They do installations across all these sectors, oil and gas, mining, pulp, and paper, and they leverage partnerships that bring in decades of fan design experience.
Yeah, from commissioning all the way to precision dynamic balancing and failure investigation. They make sure the asset not only runs, but runs optimally, exactly to the standards it was designed for, every single hour.
This has really laid out a clear roadmap for reliability. I think the core takeaway for you, the listener, is the profound value you get from shifting from reactive maintenance, waiting for the bang, and then guessing at the fix to proactive reliability, which is really about listening to the machine's first subtle communications.
And that essential shift, it's only possible when you pair that foundational trade expertise, the hard-won gut instinct of a seasoned millwright, with powerful data-driven diagnostics. This whole comprehensive service scope, from precision diagnostics and laser alignment all the way to commissioning support, that's what drives reliability, predictability, and just confidence in your critical assets, all while holding to strict standards.
The ability to find an issue in hours that had evaded engineering experts for 5 years, costing a company hundreds of thousands of dollars in just guesses. It shows the incredible value of translating a machine's dynamic story into a real, tangible, precise solution.
Exactly. It's all about data certainty.
So we've discussed how machines communicate through vibrations and how advanced tools like motion amplification can make the invisible visible. Next time you see a massive piece of industrial equipment, a pump, a cooling fan, a compressor just running smoothly in the background, maybe consider this. What subtle invisible communication is constantly happening just beneath the surface to keep that massive critical system stable? And what hidden costs would pile up if that language was permanently ignored?